Great pleasure to be presenting this evening a talk called Precipitation Reconstruction from Climate Sensitive Lithologies using Bayesian Machine Learning. This work is joint with Rohit Chandra, Nathaniel Butterworth and Deepma Muller. It's just been accepted for publication in the Journal of Environmental Modelling and Software. Okay, so the goal of this paper was to develop a model to predict precipitation from the current all the way back to 250 million years ago. And to do this, we have a number of pieces of information which must be recorded or fused in some way to give those predictions. Those information were from 4 sources, and we'll talk about them one at a time. The first source of information was sediment records. We have available, and I've listed the papers down the bottom there, information regarding the deposits of coal or evaporites or glacial deposits for various time periods going back to actually 400 million years. And they are going to be used as part of the model in which we construct to predict precipitation. For obvious reasons, coal deposits are usually associated with, higher areas of rainfall, while evaporites are normally associated with lower areas. So they are one piece of information that we do have, which can enable us to predict what happened 400 and up to 400 million years ago. The second piece of information is models for plate tectonics. What you'll see playing for you is the evolution of the continents, breaking up from a supercontinent into what we know today. The reason that we need this information is that obviously rainfall or precipitation is related to the proximity of a given latitude and longitude to the coastline, and also whether that proximity is closer to the east coast of a land. And to understand what existed at any particular latitude and longitude over the last 250 million years, we have relied on information from models for plate tectonics, which gives us their locations. So the third piece of information is reconstructed paleo elevation maps. In addition to the distance to the nearest orientation of a particular location, clearly the height of a location is related to precipitation. And we have, and I've referenced here, information regarding the elevation of the continental masses going back for 250 million years. The last piece of information is precipitation output itself from general circulation models. And we have these available for the mid-Miocene period and the late Eocene period. So for these 2 periods, we have all 4 pieces of information, that is sediment records, models of plate tectonics, reconstructed elevation, as well as precipitation. And we are going to use these 2 periods to develop a model which relates the information contained in the first 3 data points or data sources to precipitation. So to sort of summarize the data that we have, you'll see a table in front of you that relates to various eras. If you move along to the column that says time, you can see there that the time goes from about 14 million years ago, the Miocene area, all the way back to the Triassic area, which is 249 million years ago. Moving along to the next column, you'll see that the total number of observations for which we have regarding the height of a particular location, its proximity to the coast, and whether that location was on the west or east side of a landmass. They're the total number of observations. The moving across there, the N subscript DT is the number available on deposits. And you can see that we have much fewer sites where we understand what deposits were located than we do for the total number of observations. So a large part of this will be developing a model to predict deposit location. The next column, precipitation, shows you how many sites we had information regarding the precipitation. And as you just said beforehand, there were only 2 eras for which we had information regarding the precipitation. And the last 3 columns, breakdown of the number of sediment sites we had available for the different sediment types, coal, evaporites, and glacial. So you'll see, for example, the first row shows 241 of the sites that we had deposit information for had coal, 86 were evaporites, and 8 were glacial. So that's the data we have available, and we want to construct a model. As this slide says, we want to construct a model that models the joint distribution of deposits, which are denoted by Z, and precipitation, which is denoted by Y. That is, we want the joint distribution of Y and Z conditional on the data. Now, that joint distribution is equal to the marginal posterior distribution of Z times the conditional posterior distribution of the precipitation, where the conditioning is with respect to the deposit information. So we're going to develop a model for those 2 quantities. I'll just take you through some data definitions. So we have Z, as stated earlier, is for deposits with the superscript obs referring to the observed values. Obviously, we want to be able to predict the distribution or the probability of observing any deposits at sites other than where we observe them. The precipitation, that's Y. And then the spatial characteristics of the site, which I've denoted by X, and they include things like the latitude, the elevation, the distance to shore, and the orientation to the nearest coastline. Notice that longitude is not one of the spatial characteristics, and that is not to say that we don't have longitude in there, because clearly the longitude, together with where the plates, the continental plates were, is going to determine the distance to the nearest shoreline and to which side of the continent that particular site belonged. Okay, so moving on to the model for the marginal distribution of the deposits conditional on the data. We are going to assume that at any given, we're going to model this independently across time. So we're not taking the temporal dependence over time for this, and instead we're just looking at each individual time period and modeling the spatial dependence of the deposits. So we're going to assume that this spatial dependence is induced by a Gaussian process, and with a mean function, which is just a linear function of latitude and longitude, and with a covariance matrix, which is given by omega in this notation, which is the reproducing kernel in Hilbert space, which is going to be defined by a 2-dimensional thin plate spline. So then we are able to construct the probability of a deposit at any particular location, a deposit which is D, the little d there, depends upon whether or not it's evaporite, coal or glacial, conditional on its location. And instead of using a usual logit function to model that, we're using a probit function, which is, in other words, the link function is the standard normal cumulative distribution function. And the reason why we've chosen that as a computational one, it's because when we go to estimate the model, the Markov chain Monte Carlo scheme that we constructed is made much more simple by the introduction of some latent variables enabling for fast convergence of the scheme. So the model for the conditional model for the probability of, or looking at the predictive distribution of precipitation conditional on those deposits and the other covariate values contained in X. We've modeled that as a linear combination of those things, with the exception of the impact that latitude has on rainfall or precipitation. If you look to the right 2 graphs on your screen, you will see a plots on the x-axis is latitude and on the y-axis is the precipitation. The colour of the dots depends upon what type of deposits were there. The black is coal, red is evaporite, green is glacial, and the blue were locations for which we had precipitation available but no deposit information. And what you can see from these graphs, the top one is the Miocene era and the bottom one is the Eocene era. What you can see is that the precipitation, not surprisingly, was at a peak at around the equator. It drops off to the mid-latitudes where there are sort of regions of low rainfall or deserts before rising in the temperate regions and then falling again in the poles. What you can see from those two graphs is that actually using some sort of polynomial or some parametric form is not really going to be able to capture that particular way in which precipitation varies with latitude. So we have put a Gaussian process prior on that particular function as well. And so we have at the bottom there, we write it all as a linear regression where we have the linear components as discussed before, and we write the GP as a linear combination of basis functions. So we can use the general linear machinery in which to estimate it. So here's the full model in a hierarchical form. At the top, we have the observation equation, firstly for the precipitation and then for the deposits. If you prefer the graphical form, that's on the right. You've got what happens is this is the quantity that this is, conditional on Z. This is the precipitation, and the deposits feed into that model via this mechanism here. So we want to estimate these predictive distributions, which means marginalizing over the parameters that prescribe those distributions, and that marginalization is done by a Markov chain Monte Carlo scheme, where most of the steps are pretty straightforward Gibbs steps, with the odd Metropolis Hastings when the full conditional distributions are not available in closed form. So the results, what I'm about to present to you, or what is appearing on your screen, are the results for the probability of coal. In the paper, we have these also for evaporites and for glacial deposits. The dark colours represent the high probability of coal, so a value close to 1, while the lighter colours say that the probability of coal and finding coal in anywhere of that is close to 0. And superimposed upon those graphs are the dots, which indicate the actual location of the deposits themselves. And not surprisingly, where there were actual coal deposits, you'll see a high probability that areas surrounding those locations have a high probability of coal, and other areas where they don't. So, and in the paper, we also show the probability of, or show the uncertainties around these probabilities as well. Okay, so now what I'm going to do is play a video which shows how the rainfall has varied over the last 250 million years, except instead of going from instead of going from 250 million years ago to the present, I'm going to go from now all the way back to 250 million years. So I'm going to rewind that, and you can see how the rainfall distribution changed across the planet over the last 250 million years. In the paper, we go through it in more detail, and the results for the Triassic period appear here. I don't have time to go through them now, but we have a look at for each one of the periods, the Cretaceous period and the Cenozoic period. Thank you very much for listening, and I'm sorry I can't be here to join in the discussion.